Now let's get back to the business. We were analyzing a common base amplifier circuit. Okay, but let me tell you why we have discussed the common base characteristics is because in this circuit we have a common base transistor and we are going to couple our signal with ammeter, right? So it means VBE will be total VBE will be changing, because of which VCB will be changing, and we are collecting VC with reference to VB, right? Okay, we have drawn the AC equivalent circuit and simplified it. Now we can use pi or T model to explicitly see the input resistance, output resistance, and then we can write easily the relations of AV naught, AV, GV naught, and GB. So replace this transistor with this model. T model will be effective here because we have a discrete ammeter resistance, and also we have something coupled to the ammeter, and base is grounded, right? So this is the T model replacing this VJT transistor. Remember, we have neglected the early effect. There is no R naught resistance from collector to emitter, right? Now we can connect the circuit. At the emitter we have RE grounded, and we have a current limiting or safety resistance 100 ohm resistance R6, and the supply source resistance R signal, right? Or we can combine these two in series resistances to have R signal prime. Okay, so this is R signal prime. It means its value will be 175. Okay, so now at the collector you have RC grounded, RL grounded, RC grounded, RL grounded. Your output would be at this terminal, right? Which is the common terminal of R and RC and RL. At the base you have reference, right? And again new parameters are introduced, so we have to find their values. Gm is IC upon Vt, Re is Vt upon IE, or alpha by Gm. When we put all these values, we got this. We know the relation, we can find it, but we are not going to use the early effect. Now we are at the stage 2, write the gain expressions, right? So let me clear you that we have this amplifier stage, common base amplifier stage, right? Except this purple thing, because this is the injected input, right? And here the model base AC equivalent circuit of this circuit is this one, and its stage is bounded with these dashed lines, right? Part of this resistance is here because we have R6, and this is R signal, so combined to have R signal prime, right? Now we can see what is our input, output, but here base is grounded. Our input is going to be coupled at the emitter, so we have to see our input resistance to this. So it means we are watching the transistor, inside resistance of the transistor by looking into the emitter. So it means we are interested in RIE, not RIB, right? RIE. So when looking into the emitter of the transistor, what we can see that this terminal is coming as common terminal of this RE and this RE. How about the other terminal? This terminal is grounded. How about this terminal? This terminal is also grounded, right? So it means these are coming in parallel. So it means when you look into the emitter, this is the emitter junction, emitter terminal, you can see the, or the signal will see this resistance, right? Please don't be confused with this thing. This model is introduced to let you use this part separately, this part separately. This node is just a cartoon to make your job easy. So it means this is not in the circuit. So you have only this part. And when you are working with this thing, you can do that this current is going down, and through this one, if you know this current, it's going through this, so you can find the voltages. This is what this model is, right? How about the voltage at the input? So it means V signal will be, part of V signal will be appearing at this terminal, right? Some of them will be actually wasted in our signal prime. So it means our input resistance is also here. So our R input is same here, right? So whatever we found RIE, there is no other resistance RB kind of thing to make Rn different from RIE, right? So it means Rn is equal to RIE, right? How about R out? So when looking into the stage, you can see only RC, which is 1 kilo ohm, right? So what would be the Vn out of this? So Vin will be Rin divided by Rin plus R signal into V signal, right? And what is Rn is RIE, right? So VE will be developing across Rn, or we can say across RIE. So it means for this, out of this V signal, Vin is developing here, its positive terminal here is negative terminal here, and it can see basically this Vi will be at the parallel combination of these two resistances, not only this, right? So you have to fold it down because this ground is here, so this ground will comes here, and this terminal will be common for this RE and this thing. So you have Vi across RE and this small RE. Let's draw it here, right? Then what about VBE? So Vi has positive terminal here, negative here. So if you bring it down, this will be here, right? Ground. So it means VBE wants to have negative terminal here. So it means VBE is nothing but negative of Vi, right? VBE is minus Vi. So it means we can use Rin divided by Rin plus R signal to V signal with minus sign, right? And Rin is nothing but RIE you can put here, right? So how about the output voltages? So output voltage will be equal to, if we want to write at the output of the stage, not including the RL, then the current is flowing through RC is GMVB. So GMVB multiplied by RC, but this terminal voltage we want to write, and this is the current leaving terminal, current entering terminal is this one. Because this arrow is showing that this current is going down, it means it is coming here to here. So that's why we have minus sign here. We already know that with the common ammeter configuration, right? How about V out here with RL will be the same, but at this time, because you connected another resistance, the parallel combination of this resistance is actually carrying that current which is going into the collector. So minus GMVB are not parallel to RL. Okay, so I'm not going to show you what would be the AV naught, AV, GV naught, and GV. Please do it yourself. I just make a hint for you. Input of the stage, output of the stage, AV naught. Input of the stage to the RL, AV. Source to the output of the stage, excluding RL, will be GV naught. From input to the output, the overall gain is GV, right? At this time, I'm going to write the expression and finding the numerical values of AV and GV, not AV naught and GV. Please do it yourself. So for AV, from input of the stage to the output with RL, right? So it means I have to consider this equation. V naught is equal to minus Gm VB R naught parallel to RL, right? And from input of the stage to this one, it means we want to have VI here, right? So we have to replace VBE to bring something related to VI. So we have this relation. VBE is nothing just equal to minus VI, right? So minus minus pick plus, right? So now we have AV is V naught by Vn Gm R naught parallel to RL, right? And when we put all these values, we got 114.8, very high gain, right? How about GV? So GV will be from here to here, including R naught RL. So it means we have to consider this equation again. We have considered it, right? But at this time, we want to replace VBE with V signal so that we can have a relation from here to here, right? So we have this relation. VBE is this one. Sorry, we have a minus sign here, right? We would be having a minus sign here. So it means minus minus plus Gm Rn divided by R signal plus Rn into something like that. We can bring this V signal down to have a relation of VGE, GV, and we have all these parameters. When we put these together in this equation, we got positive gain of 2.77. What is the meaning of positive gain? Negative gain was because we have 180-degree out of phase signal at the output with reference to the input. It means here we are having no phase shift. Our output will be following the same phase as of the input signal. Okay, so before we go further, let us show you the simulation of this circuit. We have drawn this circuit, right? So this is not connected, right? In the slides, we have this terminal drawn behind, right? So, but here there is no connection, so this circuit is same, right? And we have just mod programmed it for transient analysis. So this is our input, 1 millivolt. This is our output, right? 2 point, please see here, 2 point, just Y value is 2.749, right? The output is 2.749, 2.77 gain. It means if we multiply V out by V signal is 2.77. So V out will be this GV multiplied by V signal, right? So V signal is 1 millivolt. So 1 millivolt multiplied by this is 2.77 millivolt. And in simulation, we are getting nearly that value, almost that value, 2.75 millivolt. Okay. So plot GAV yourself, find AV naught and GV naught yourself.